Yes. Okay. So the recording has been started. Yeah. So yeah, today we will be actually again brushing through some of the concepts of regression. Rather, I mean, it shows. Yeah, I mean, somebody is saying, please turn on pointer, laser pointer while sharing the screen. So I think it is not required because I am using these sort of things, right? Sorry, where is it? Yeah, these. So that's the point. And another thing is, I am not totally sure whether in tab that can be done. So I hope this is fine. I mean, just writing in this way, right? Anybody has any comments on that? Because if I go to on that laser pointer thing, I have to go to my laptop. There I won't have the marker. So which one do you want, Sujit? You can let me try to unmute you. Sujit. Yeah, Sujit, I have requested you to unmute.
Okay, sir, it's fine.
Okay, thanks. You can mute. Okay, now, yeah, so all the logistics related thing I said I will take at the end of the class. Okay, so let us quickly go to this whatever we are supposed to discuss today. So though it is saying logistic regression, it's basically I mean linear regression and logistic regression. So we will first go through linear regression, its univariate case, then multiple variables, and then we will go to logistic regression. And in between, actually, that's an important thing. Yeah. So this is the agenda. We will brush up concepts of maximum likelihood. So probably in your typical machine learning courses, you might not have encountered maximum likelihood, or rather, I would say the connection between maximum likelihood estimation and the linear regression in under Gaussian noise assumption, right? So that we will quickly see. And regression and classification with linear models that you must have done in machine learning, which was a prerequisite for this. And I mean, we will just quickly go through it. Same goes for logistic function for binary classification. So let us, without any further ado, let us dive into it. Yeah, so these are the, I would say, canonical references for that, the elements of statistical learning by Hastie, Tipsarean, and Friedman. It is free completely. Link is available. Chapter 3 and 4, artificial intelligence. This is probably the 3rd edition, which is free. The 4th edition has come, which is not free. So from chapter 18. So some of the stuffs, yes. Again, it's not always that I have followed diligently all of it, but yeah, some references you will find. And whatever you have learned in your machine learning courses, whatever references that you have followed there, that will also serve the purpose. Okay, now quickly to linear regression. You know what is the regression and what is the classification problem. So in machine learning probably starts with such a class, right? So in regression problem, you want to find the relation between some input variables X and some output variables Y. So basically you want to find a relation between X and Y, where X can be in RD, Y is generally in R, but that also can be taken care of. Y can be in some R, M or Rn. But we will focus on a scalar Y, that is scalar output on this, right? So inputs are also often referred to as covariates, predictors, or features. I mean, correspondingly, the outputs can be referenced as variates, targets, and levels. So different books refer it in different way. I see Kaushik has a raised hand. I'm just asking him to unmute. Yes. Any questions? Oh, I think her hand has been lowered. Okay. Yeah, if you have any questions, raise your hand. I mean, logistics related questions I will take at the end of the class. Okay, examples of such input-output pairs, that is basically some examples of problems that we deal with in linear regression or regression, so to say, is suppose you have, you need to know the energy requirement of say a classroom. So what is the outside temperature? What is the number of people inside the classroom? Target room temperature. Maybe depending on that, you need to turn on a heater or turn on a AC, and how much temperature you want to target basically. So for depending on all of these, you need an energy requirement. So that's a scalar, some kilowatts or something of that energy. And outside temperature, people inside room, target room temperature, these can be taken as your x's, right? And this is y. Similarly, say you want to know what is the size, or what is the price of some real estate building. So size, for that, the input that you need to give is the size of the floor, I think it is called, and then number of bedrooms, number of floors if it is a house, say, age of the home. So if it is getting, say, resale, so what is the age of the home, etc. Those are all your x's, and your y will be the price. So let us just take a look at the how does it look in a plot. So this is for a particular, say, x like this, and y. And I mean, for visualization purposes, you have to basically I mean, I'm just showing it for a single scalar x, that is x d, where or x is rather in r, that is d is 1. So only one component of x is there. So it can be anything like this or this, but only one x, maybe the outside temperature and energy requirement, maybe just the, say, number of bedrooms and price. So x is that one of the x's. So this is just for I mean, visualization purposes, and we will start with that our analysis. So x and y both are scalars. So one input, one dimensional input and one dimensional output. So this is xi and yi. So I mean, these are the observation or points. So for a corresponding x, this is the y. I suppose that, okay, maybe not temperature is not a good range here. Say the square feet. Square feet is a little less than 1,000, so it is like whatever, 200. I mean, then this is whatever, not 2 lakhs. So yeah, 200 into 10,000 something. I mean, the unit. So you get the idea that for this particular 1,000, this is 200, close to 200 or whatever, 190. For this was probably 1,200, and for that it is 200, and so on. This type of this is the general plot, and you have to find some function, some hypothesis which will give you, or which will enable you to find y from x, that is from an unknown x. Say I'm denoting it as x star. From that, and what will be the y star. So these are given in your as your training input. So x1, x2 to xn, y1, and the corresponding y1, y2 to yn. And for an unknown, or rather for an x star for which y star is unknown, you need to find the y star. Now I see a raised hand. Yeah, Kaushik, I am asking you to unmute. If you have any questions, please. I have asked you to unmute. Yeah. I cannot hear anything. Hello. You have any questions? I cannot hear. Maybe you can write it in the chat in that case. Oh, I think I heard some noise. Okay. Anyway, let us move ahead. So the input and so the input and output variables are assumed. So this is important. Assumed to be related via a relation known as a hypothesis. So this is known as hypothesis. But yeah, I mean, they are assumed. So you don't really know the real relation. That is what is the relation between y and x. But you can assume some. Yeah. Kaushik, you have some question? No? Yeah, maybe then you can unmute. I mean, I cannot hear.
Yeah, I know. I just wanted to
Yeah.
clarify that is the sound okay? Because I can
Sorry.
I can hear a lot of breaks in between. I don't know if it's on my side or.
Sorry, your voice is too much dropping. Maybe you can write it. Try to write it in the chat if that is possible. Otherwise, your voice was dropping too much. I did not understand the question. Okay. Oh, somebody is saying, Sagar is saying he cannot hear. He has internet issues. Oh, maybe it may be. But yeah, it is getting recorded. But I hope, I mean, I asked everybody to, at the beginning, whether you can hear me. So just I am allowing for the time being to unmute yourselves, everybody. And just let me know if you can hear me good.
Sir, you're audible properly, sir.
Okay.
Yes.
Then
Yes,
probably
sir.
it
You
is
are
some
audible.
internet issue. Yeah.
Yes, sir.
Okay. I'm going back again. So the input and output variables are assumed to be related via the relation hypothesis. So the important words are assumed and this definition hypothesis. So y is some h theta x, where theta is the parameter vector. So it is parameterized by that theta vector. So theta is your now something that you want to know, because if you know theta, then you know the whole h theta. So if you input any x, you will get an y. So that is what is written in the next line. The goal is to predict output variable y hat star is equal to f x star for an arbitrary value of input variable x star. So for an input variable x star, you want to know what is the predicted output. Now, why I have given hat, this is because this is just a common notation that since it may not be the actual value of y. So what if you had known the actual value of y, it may not be equal to what you are predicting by the hypothesis. So that's why this hat notation is given, that it's just the predicted value. So let us start with some scalar inputs x and scalar outputs y. As I said, the univariate linear regression case. So yeah, so univariate linear regression, as I said, the topic of the slide. So hypothesis. So you have scalar x and some y. Okay. Now hypothesis is that okay, it is related in a linear form. So for a scalar x and scalar y, the linear form is this: theta 0. It's kind of the slope intercept form. Sometimes it is called an affine relation. You will find all these terms, but the crux of the matter is that you don't know, or you want to estimate two parameters, your theta 0 and theta 1. So h theta is of this form, theta 0 plus theta 1 x, or rather you can just think of it as a function of x, which is parameterized by these theta, and theta has two components, theta 0 and theta 1. So I mean, we will come to that component vector, etc. Just for the univariate linear regression, you think that it is there are two values of theta that you need to estimate, the theta 0 and theta 1. So it just defines a linear relation. Cost function, because you know from our previous discussions that you need to find some sort of a distance or disagreement of your predicted value and the true value that you are given as a training data. So if it is coming perfectly fine, then you don't have to learn anything. I mean, for a particular value of theta, if your all your xy pairs that are given as your training, if you pass all those x's through h theta x, that is pass means you just put those x's for that corresponding theta 0, theta 1, and you find the corresponding y's. These y's, you remember, these are y hats, right? These are predicted value. And if these y hats are exactly similar with the y's, then you have nothing to do. I mean, you have found your theta 0 and theta 1. But if not, then you need to minimize that distance, some sort of that disagreement. And that one of one of the standard sort of disagreement metric is this cost function. I mean, this sum of squared errors. We also call it as a cost function, right? So sum of squared errors, as it says, it is just like this. So h theta xi is your predicted value, yi is your true value for the corresponding xi, and you are just squaring the difference between them and then summing, or you can take an average, right? So the thing is that this is, I mean, this is in accordance to our previous notation of J, right? And this is a function of theta 0 and theta 1 because we want to minimize or find the minimizing value of theta 0 and theta 1. Now, the thing is that what are i's here? So xi, yi, that means you have, so you see i's from 1 to n. So this sum goes from x1, y1, x2, y2 to xn, yn. That means you have n training data. So n xy pairs you have been given, and you are trying, you have been asked to find the hypothesis. So optimization objective is find model parameters that will minimize the sum of squared errors. This is all you know. Now you know what to do. So we have discussed a lot about this in optimization. So find the gradient of this cost function. So if you try to find the gradient of this cost function with respect to theta 0, of course you need to put some of your skills of like finding the derivative. That's basically the chain rule, right? So it's, if you are trying to find the partial derivative of this j theta with theta 0, then you need to, like, I mean, it's the gradient operator is linear and the summation is linear, so the gradient goes inside the sum, and you then operate the gradient on that. And if you apply the chain rule, then this and the derivative of basically this thing with respect to theta 0, and then sorry, with respect to this inside, and this inside thing with respect to, that is h theta with respect to theta 0. And if you take the derivative of h theta with respect to theta 0, it is 1. So that's why it is not written, but it is actually multiplied with 1. Similarly with theta 1. So the second term of the chain rule will give you x. So it is xi, right? So these are just the two gradients. So you know, you can solve this is just linear equation. So you have theta 0 and theta 1, two unknowns and two equations. You can just try to solve it. So if you do this tedious math, hopefully you will arrive at this. I have done it in hand, so maybe just you'd like to check whether this is right or wrong. But that's the sort of thing that puzzles everybody, right? Or makes you skeptical. Okay, whether I have done it right, whether it's okay. So for that, what you can do is the gradient descent, right? So yeah, so that yeah, I'll come. But yeah, I mean, you can find it in this way, analytical form. But you can also do, because you have the gradients, you can do the gradient descent, because that is just, you start with some theta 0, theta 1, or even yeah, theta 0, theta 1. Then you basically you have the gradient. So for that theta 0, theta 1, what is the gradient you compute? Then your corresponding theta 0 minus epsilon times this, and corresponding theta 1 minus this epsilon times this. So that you can do always, right? Now, yeah, so this is the form. Now, quickly, I will go to multivariate linear regression. But before that, if you have any questions, please raise your hand. Yeah, I think I am finding it. Raise hand. I am asking you to unmute, Anupam. Yeah.
Sir, can you go back to the earlier equation, the one above that?
This one?
Yes, sir. Sir,
Yeah.
so in this case, you're saying that we can just directly compute the values of theta 0 and theta 1 that optimize the loss function for all of our n variates, right?
Right, yeah.
So will we get the same answer if we use gradient descent in this case? Like, will the answers be similar?
Yes. This is like very well behaved cost function, just linear. This is a convex actually cost function. So it has one single minima. So if you run your gradient descent to infinite iteration, basically, I mean, if you want to know that whether exactly to what precision I will get, so for that you need to, of course, run infinite times. But any reasonable value close to it, you will get within.
Sir, so in what kind of cases can we directly apply this formula versus like in what kind of cases?
Yeah, this is the univariate linear regression. I mean, this is the solution for univariate linear regression, where you have x and y, that is scalar x and scalar y. So if you have any scalar x and scalar y, like y is equal to fx sort of data you have, and you don't know f, you want to know f, but you have to assume that y and x are related in a linear fashion. Then
Okay,
you
sir.
can use that.
Okay, sir. Okay, sir. Thank you, sir.
Okay, I see that somebody has asked in chat that said there is no partial derivative operator. Yeah, it's basically understood that these are partial derivatives. So from the context, you just oh, okay, yeah, I think yeah. That's a typo. Yeah, so del and so on. Yeah, so I'll update that. Yeah, that's just a typo. Yeah. Okay, let me go to multivariate linear regression. So now we are like going a scale up, which says that we can easily extend to multivariate linear regression problems. So still the hypothesis is linear function of x, where x is Rd. Now d can be greater than equal to 1. So basically greater than 1 because d equal to 1 we have seen. So now the hypothesis in a linear form is one of the hypotheses can be this form. Sorry, it was previously only theta 0 and theta 1 x1 because or theta 1 x rather, because that time it was just scalar. But now x is a vector which has say d components x1, x2 to xd, right? So you have to basically find theta for every of these d dimensions plus this constant theta, right? Or rather the constant term. This is the bias term you will see. I mean, we'll connect it to the neural networks probably next topic, not next day, tomorrow, but next topic. So so theta 0, theta 1 x1, theta 2 x2 till theta dxt. So now you have to find all these thetas. So theta 0, theta that is theta 0, theta 1, theta 2 to theta d. So for a d-dimensional x, you need to find d plus 1 thetas, components of theta. I mean, theta can also be thought of as a vector. We'll come to that. So for convenience of notation, let us define x0 as 1. Though we don't have an x0, I mean x1, x2 to xd for a particular x. So this is for a particular x. I don't have an option to like boldify this. Maybe I will write one bar whenever is required. I mean, if from context it is clear, then it's fine. So it is actually small x. Okay. So this, yeah, but yeah, I think it will be clear from context. So for convenience of notation, we are defining x0 as 1. So we are actually telling that our x is not just this d, but there is a x0 which is always 1. So it's a d plus 1 dimensional vector now, right? So H is simply just the dot product of the parameters and the input vector. So it is theta transpose x. This H theta x can always be written as theta transpose x, where theta is your theta 0 to theta d, that vector, and x is your x0 to xd, that is the vector. Now the sum of squared errors. So this is a dot product. This simply is just a scalar. So dot product is a scalar. This H theta x or this H theta x, whatever may be the way you can think about it. Now cost function is the sum of squared errors. That's we have defined. So same thing. So H theta x minus yi. So H theta xi minus yi. So again, i's are the like running index for the number of training examples. So then the data that you are given, and that number is n. But now it is a function of the big boldified theta, which is theta 0, theta 1 to theta d. So you take the square of it. Now we will use the following, that is basically this. We will use this to write the cost function in a compact matrix vector notation. Let us see how it is done in the next slide. So this is the cost function for a multivariate linear regression. For a single variate linear or univariate linear regression, we have seen it in 2-3 slides back. Now you see, just think about what is this H theta x1. So this is like the multiplication of this row and this vector. So this is this row of that matrix and this vector. So it is x01 theta 0, x11 theta 1, x21 theta 2, right? So that is what we have seen here. So theta 0, then that is theta 0, x0, theta 1, x1, theta 2, x2. So theta 0, x0, theta 1, x1, and so on. So we can like write this n values of the predicted or n predicted values in a vector in this form. So h theta x1, h theta x2, h theta xn, and the corresponding right hand side will be a matrix vector notation. So this is our matrix vector product. So this is the matrix of all the x's, all the components of x's, and or all the components of all the x's, and this is the vector of all the components of theta. So x is now a n cross d plus 1 dimensional, because what we have seen is that after adding that x0, which is always 1, x becomes d plus 1 dimensional, and you have n such rows because you have n data here also. So it is n cross d plus 1. With each row is an input vector. What do we mean by input vector? That is the the short term or notation of the input data in the vector form. So input data is x, because your h theta takes x as the input. So these are like all connected. So that's why this is called an input vector. So each row is one input vector. So this is the first data, this is the second data or second x, this is the last nth x, right? Y hat is an n length vector of the outputs in the training set. So this, remember that y hat is also an n length vector. So when we went from univariate to multivariate, what did we change? That x is a d plus 1 vector now, and y also can be represented as a n length vector, right? So this we will use later when we will compute the solution of it. So let us go ahead. Oh yeah, it is in the next slide. So so equation 1, which is this, that is the sum of squares. So later, what did we say here? We will use the following to write the cost function in a compact matrix vector notation. So this cost function we will try to write in a compact matrix vector notation. So this is the equation 1. We are trying to write it using this equation 2. Let's see. So this is just the exact copy of equation 1. Now theta transpose xi is y hat I. That is what we have told here, right? Because h theta x is your theta transpose x, and h theta x also we are denoting as y hat x, sorry, y hat of x. So this is like y hat 1 for x1, y hat 2 for x2, and so on. So theta transpose xi is y hat replaced with y hat xi. Now this is what did we say here? Y hat is a n length vector of the outputs in the training set, and what are you doing here? You are basically summing the, say, y1 minus that is y hat 1, this is y1 square, plus y hat 2 minus y2 square, and so on. So you can think that this is the norm or 2 norm of a vector whose elements are y hat 1 minus y1, y hat 2 minus y2, and so on. This can be the this can be thought of as a vector. So that's what we have written. So this is, and this is what this. Let me go to a different color maybe. So this part is your y hat vector, and this part I am calling the y vector. That is, we are collecting all these y hats in a vector, and we are collecting all the y's in also a vector, right? So this is y hat minus y, it's 2 norm square, right? So now for any vector, for a vector A, the 2 norm square is, this is A transpose A. So that's what I have written here, right? Now 1 over 2n, this is, now this y hat is your theta transpose or x theta rather, because y hat vector we have seen here is this. So y hat vector, we are just replacing it with x theta, right? Now you are just doing algebra. So just multiplying these two terms. This is what is coming. Now, notice these two like differently colored terms. So this is x transpose y. What is x? It's a matrix and y is a vector. Now you are multiplying x transpose with y. So that's a vector because it's a matrix and it's a vector. So now, and theta is also a vector. So what, I mean, I'm just calling it as a. So theta transpose A, you can write it very similar to as A transpose theta, the same thing, because theta transpose A is a scalar. That is the inner product between theta and A. Similar is A, or same is A, the inner product between A and theta, right? So this is okay, yeah. So this is what we are doing here. So this, instead of A transpose theta, we are sorry, instead of theta transpose A, that is this line is this and this line is this, right? I hope this is clear. If not, I'll stop after this slide. Then y transpose x. Now, what is this, or how can I write this? So suppose y transpose x is your A now. So what we have now is, or yeah, so y transpose x is A. Now A can be written as A transpose transpose, right? So that means y transpose x, this whole transposes, again transpose. Now if I go here, the inner thing will be x transpose y, and then the outer transpose is there. Hopefully this is clear, right? So you are just writing it as the transpose of its transpose, right? And then you are using the transpose rule. So now you have, if you notice these two terms, that is these two terms, they are same. So basically 2 into this, and this term is there. So you have found the j theta. So what is your next step? You will try to find the gradient of j theta. So this is a quadratic form, theta transpose some A theta. This is 2b transpose theta, and this is y transpose y. So all these formulas were given as a brush up of the linear algebra primer. So these are the, I mean, when you are taking the gradient, you are getting this y transpose y is, of course, I like, it does not depend on theta, so it is 0. So x transpose, so if you just do this algebra, it will come as this. Now theta is this. So x transpose x inverse x transpose y. So yeah, I will go to this and the next slide, and then I'll stop for the question. So this gives a closed form solution, but another, what is a closed form solution? It's just the analytical solution. By doing the math, you get it. But another option is, of course, to use the iterative solution, that is the gradient descent, just like the univariate case, because you have this grad j theta, which is this. So if you do this, you will just like the univariate case find this. But what is the advantage or disadvantage of both of them? So iterative gradient descent or iterative method needs to perform many iterations and need to choose a step size parameter judiciously. So the step size parameter is of utmost importance. You may otherwise overshoot. But it works equally well even if the number of features D is large. Why having D is large is a problem in the analytical solution, we'll see, or we will just come. So for the least square solution, there is no need to choose a step size. Of course, you are directly going to the minima, and no need to iterate. But evaluating this can be slow if D is large. Why? Because what is X's dimension? We have seen it is n cross D plus 1. Somewhere it was written. Yeah, so n cross D plus 1. So X transpose X will be, n cross D plus 1. So X transpose X will be D plus 1 cross D plus 1. So inverting a D plus 1 cross D plus 1 matrix will be of the order of D plus 1's cube, right? So if D is high, then this inversion computation cost will be high. So that's the issue, that if you have smaller or lower D, you can directly go for this. Otherwise, I mean, this is always an option. I mean, the iterative gradient descent. Okay, let me see. Yeah, I'll stop for the question. Yeah, if you have any questions, you can raise your hand. Yeah, so Subham is saying, okay, let me try to unmute Subham SHU. Yeah. Yeah. What is your question? Can you use the multivariate? Yeah. So yeah, I think you got your answer that you can also get an equivalent analytical solution for multivariate. So that's good that you are thinking what can come next. Okay, Sijanak Day, should the cost function for linear always be square? No. It can be any. I mean, it can be L1 norm. It can be many things. I mean, it's just one of them, right? Can you hear again why we divide by 20? Yeah, it's just convenience. I mean, if you try to find the cost function. So where is this? The cost function. So this is in whatever you are dividing it with, it does not affect the argument. So if you are trying to find, or minimizing argument rather, so j theta, you are trying to find the arg mean or arg max with respect to theta. This is same as arg mean j theta with say some k constant. Okay, so the same theta minimizes it. But if you have these two, basically these two gets cancelled, and this is just mathematical convenience. So these two, you see, these two get cancelled. So it's just a mathematical convenience, nothing else. Is the cost function used here convex? Yes, it is convex. You can try to prove it, but yeah, for linear regression with the squared squared error, it is convex. So it means that gradient descent will work as good as direct computation, and that too in lesser time as compared to formula. But yeah, so we should always be using gradients, or does formula has some benefit over gradient descent? Yeah, I mean, I said whatever the summary I told, that for linear regression, you can always use your gradient descent, because I mean, you can use either depending on your use case. If you have a large D or not. I mean, both of them will give very close values. As I said, I mean, for mathematical, I would say clarity, or rather mathematically to be mathematically correct, I must say that a gradient descent needs to run till infinite iteration. But for all practical purposes, you can use it. For large variety, it is more useful to employ the multivariate linear regression rather than gradient descent. I mean, multivariate linear regression is the problem, and gradient descent is the solution methodology. Another solution methodology is an analytical solution or closed form solution. So I'm not totally sure about your question, Rishabh. So let me, Rishabh Chaudhary. So let me try to unmute you. Ask to unmute. Yeah, Rishabh Chaudhary, what is your exact question? Yeah, I have asked you to unmute, Rishabh. You can unmute.
Yes, sir. I meant the one you said. I mean the closed form solution versus the gradient descent.
Yes. So in multivariate linear regression case, or any linear model rather, you can always try to find an analytical solution. Now, the thing is that how easy is to find that analytical solution, then how computationally efficient it is, and so on. So for at least these special cases, for multivariate linear regression, they work equally well. For smaller D, probably going for analytical solution is more easy. But for larger D, always gradient descent is an option that you resort to, because here the analytical solution is easy. I mean, it's not very cumbersome in terms of math, that you can basically do mistake in that math. So, but that can be some cases in some other linear models, not say this sort of linear hypothesis, then your squared error. If suppose those are not there, that may be cumbersome. That's the thing. Okay, I see another Rishabh Tripathi, but inverse won't always exist. That's a very good question. So I would actually let you figure out what is the condition for this inverse to exist. This should be covered in your machine learning course. If you find anything, just tell me in Piazza. Okay, it's very easy. I mean, probably all machine learning books have. Okay, I'm just giving some hint that some sort of a linear independence assumption is required. Okay, I think let me go ahead with the idea of linear regression as maximum likelihood estimation. So far we tried to fit a straight line, that is a hyperplane to be more precise, for higher dimensions for linear regression problems. So this is the sort of modeling that we have tried to do. This is in a sense a constant. I mean, again, I'm saying in a sense a constant way of looking at the problem. The thing is that the data points may not be exactly fitting or perfectly fitting to the hyperplane. So if we can actually model the noise that, okay, this is a hyperplane, so we are getting some hyperplane, but we know that that hyperplane does not exactly fit. So we can add some noise to the hyperplane to get the exact fit. So if we incorporate that in the modeling, then what we arrive at is a probabilistic interpretation of it. And the probabilistic interpretation, at least for linear regression and Gaussian noise assumption, we will see that it exactly is same as the linear regression cost function interpretation, so to say, the one that we discussed, with squared error cost function. So basically what I mean to say is, I mean, the probabilistic interpretation is always there, and if you satisfy some noise assumption, some hypothesis assumption in both the probabilistic interpretation and the non-probabilistic, so to say, interpretation, it can be shown that they are equivalent. So let us at least go into one such case. Okay, I don't know whether this has been covered in your machine learning course, but let's try to dive into it. Okay. So an alternative view, that's what I said, an alternative view considers the following, that yi's are generated from xi following an underlying hyperplane, but we don't get to see or observe that I discussed last one of the classes, earlier classes. We don't get to see the generated data. Instead, we see a noisy version of yi. So that is, I mean, both the line now include your hypothesis that, okay, it is coming from an underlying hyperplane, but what you are seeing when you are measuring it, when you are measuring the temperature, when you are seeing the price, it has some noisy component. It's not just all those x's that are given to you. That is all those x components. There may be some other variables which you can never know. So instead, see a noisy version. So that is actually, all those are modeled as a noise. So instead, we see a noisy version of yi. Maximum likelihood, or in general probabilistic estimation, models this uncertainty in determining the data generating function. So I'll come to what we mean by maximum likelihood. It might be a little familiar, or rather familiar with people who have taken, say, estimation theory, or more, I think, advanced probabilistic probability theory courses. But yeah, it's just a brush up again. I just wanted to show you the connection between this probabilistic estimation and the non-probabilistic estimation, so to say. So thus the data are assumed to be generated as follows. So it is not just previously what we were thinking is yi is h theta xi. Now we have this noise part, right? This is epsilon I is the noise corresponding to the ith data. So where epsilon I is an additive noise following some probability distribution. So xi yi's form a joint distribution, suppose, of course. So this since yi is epsilon I is a noise, then basically even if x is deterministic, yi is basically probabilistic. So xi yi forms a joint distribution. The idea, I mean, it is just like a, I mean, if you try to convince yourself, then maybe you can go back to your linear Gaussian models that you have studied in your probability courses, right? So you have a Gaussian noise. If you add it to some constant, the resultant also becomes Gaussian, right? So the idea is to assume a probability distribution on the noise. Idea is to assume, again, these are the important terms, a probability distribution on the noise, and the probability distribution is parameterized by some additional parameters. So say the probability distribution is Gaussian, though, so you can assume that, okay, I know the mean, maybe somebody tells you that, okay, 0 mean, and covariance is sigma square. This covariance sigma square is now again one of your unknown, in addition to your the thetas, the h thetas. So find the parameters of both theta and sigma square that is most likely to generate the data. So what this will give in addition to you, so you are only getting the thetas. Now you will get the sigma square. So previously you were getting this y star corresponding to x star, which was h theta x star. So when you are, as a machine learning practitioner, you are giving that, okay, if you give me that this is my suppose you are dealing with that price prediction for house, right? That problem. So somebody has given you the number of floors, the year of the home, etc. In terms of this x star, and say the square feet area. So you are computing the y star because you have the h theta. This is your non-probabilistic approach. But if you have this probabilistic approach, you can also give the sigma square. That, okay, I am giving you this, but I am not too certain. There can be a plus minus sigma value. So this is much more, I would say, people will like to say believe you more. Okay, so it's not that only this will always have that this x star will always have this value, but at least he's giving me some uncertainty that, okay, I am sure within this confidence threshold. So you know about this confidence threshold and so on, right? So that is the idea of the probabilistic. I mean, I mean, you are also doing a bit more math, of course. You are trying to find this sigma square, but at least you are being able to give more information to the customer, right? Now, let me just go ahead with these two slides, and then let me actually go ahead with this, and then I'll stop at the end for the questions. So this is the cost function based approach. So this is just, so this is just the overall view of how do you approach a cost function based problem. So this is training set. It is saying xi, yi, that is given, and this is like the algorithm that you use, or the methodology that you, not the algorithm, the methodology that you use. Find theta, which minimizes the cost on training data. So this is the training data, and this is the cost function. So of course, you need to give information to this methodology. What is the training data or training set, and what is the cost? So that you are giving. Now you find this h theta. Depending on this training set and cost function, you find this h theta. Then you give any unknown input x, you get the output y. Now, this alternate view, that is the maximum likelihood, the red parts are basically the changed part. So you see, this is training data, and then cost function you are giving. Here it is the probability, the joint probability distribution. For that, you need to just give the probability distribution of the noise, which can be Gaussian or anything else. But Gaussian is always simpler to find, say, from other probability distribution. What will be the joint distribution may be cumbersome, but it is doable. Now find theta, which maximizes probability of the training set. So that we will see how to do this, because we have seen this methodology. Find theta, which minimizes the cost of training data. You find the cost, you find the derivative, then you can either try to go for analytical solution by making the derivative equal to 0, or you just do gradient descent. So similarly, we need to do something which is telling that find theta, which maximizes probability of the training set. What is that? We will come. Then, then we are getting the same h theta. You give input x, output y, and along with it, you can give an uncertainty set. Now, maximum likelihood example, I think it's better if I go there. I'll come back to this, maybe not today, but it will be better if I can intuitively basically explain this first. Suppose, what is, again, I mean, this is probably too basic for people who have done estimation theory or maybe advanced probability case, but let's try to see what we can know. So we have n is equal to 3 data points. That is, you know that your y's are coming. Forget about x, anything. Just you have one single dimension of data, y, and that y, somebody has given you 3 data points, just denoted by y1, y2, and y3. And these values are 1, 0.5, and 1.5. So 3 scalar values, which are independent and Gaussian with unknown mean theta and variance 1. And people, I mean, whoever has given you this has said that this has been drawn from a Gaussian with mean theta and variance 1. So variance he has given you as 1, but the mean is unknown. Now you are asked to basically find the theta, and you are given 2 choices. Say consider 2 guesses of theta, 1 and 2.5. Which one has higher likelihood? That is, which one is more likely to be the right theta given this data? So I am just trying to allowing unmute for yourselves. So can anybody tell which one is more likely?
1.
Yes. And what is the intuition? If I am asking you, what is the intuition?
So we see most of the values over there are around the 1 range. So 2.5 would be very low probability.
Exactly. So that is the thing that is given by the next slide, and that is the idea behind the maximum likelihood. So if you see, so here that consider, so finding theta that maximizes the likelihood is equivalent to moving the Gaussian until the product of 3 bars is maximized. So Sayan has said that the probability of these y1, y2, y3 is more if I consider theta as 1. So that is exactly what is, you can see that if theta is 1, then the probability of y is equal to 0.5 is some value this. The probability of y is equal to 1, that is this, that is this probability, somewhere this, and probability of y3, that is 1.5, this is this value, right? So what is the joint probability of these 3? It is because they are independently drawn from that same Gaussian. So this is the product, I mean the likelihood, or again the term likelihood I am defining later, but the probability, joint probability of them is the product of these 3 probabilities. So the product is higher here compared to here, because the same 0.5, 1 and 1.5, you are getting these values, right, as the probabilities, and this product you definitely see it is, I mean this right hand product is definitely less. Now so that is the basic idea, again the intuition behind maximum likelihood. So you what is likelihood? It is just the probability parameterized by the theta, that is parameterized by the probability distribution assumption, from which probability it is coming. It has some parameters. So if you just write it with this colon, I mean, it is called the likelihood. There are some legacy reasons and etc. So Bayesian and frequencies, etc. If you are interested, you can go ahead with any standard statistics textbook. But for your purposes, just remember that likelihood is the probability parameterized by theta. And I mean, you can, for all your practical purposes, I mean, when you are doing the maths on the probability, you can forget this notation. Just py1, y2, y3 would do. Here py1, py2, py3 would do, but it will be coming as a function of theta, right? So that you need to play with if you want to minimize, maximize. So you are getting this as your likelihood, or the joint probability distribution, which is a product of the individual probabilities. So you see which one maximally is probable or likely, maximally likely. So this term maximal is coming, right? So you need to do some maximization, some optimization. So you need to basically find the theta which maximizes this. So again, it comes to then optimization. So let us go ahead. So in general, this is the general recipe for maximum likelihood estimation. So in general, we have observations, some data which was written as y1, y2, y3 earlier in the last slide. We assume the data is generated by some distribution, right? And then compute the likelihood function. So I mean, it's the same thing we did here, right? We are assuming that this is generated by Gaussian, then compute the likelihood function, that is just the product of the individual probability values for those n data. So here is n, this is the likelihood function. That is what we have defined here, right? Now theta ml again, I said that you need to go to some sort of a maximization. So theta ML here is maximum likelihood. The theta that that is the makes this as a, or rather this, the maximum value, we call it maximum likelihood, because it is making this maximally likely, this L theta, or rather this joint probability value as the maximum. So R max L theta over theta. So okay, and this is just again for mathematical convenience. Log is a monotonically increasing function, so whichever is maximizing L theta, the same theta will maximize the log of this thing, right? So if you and log, if you distribute among the products, it becomes sum. So this is just I mean algebra. So this is likelihood function, this is the log likelihood function which you need to maximize, since this is a monotonically increasing, same as R max as fx. So this is the general recipe for finding a maximum likelihood solution. Now if I quickly go back to this, I will come back to this tomorrow again, but here I think, yeah, yeah, let me at least define the problem, and then I'll just ask you to read this through, because the slides are uploaded, and then I will complete it. So tomorrow. So intuitive example again, estimate a coin toss. I have seen 3 flips of heads and 2 flips of tails. What is the chance of head or tail to my next flip? So suppose this is the experiment that I am trying to do, and the toss, the coin, I don't know whether it's fair or biased or no. I am just trying to find it from experiment. So your data is, you have tossed it for 3 or 5 total tosses, flips. Out of them 3 are heads, 2 are tails. So what is the chance of head or tail in my next flip? That is you want to know the probability of heads or tails. So I mean, you know that, I mean, from your very basic statistics classes, that okay, my heads probability is 3/5, right? So can we do it or justify it in a maximum likelihood? So for that, of course, what is the general recipe for maximum likelihood? You have to assume a probability distribution, right? A model. So the model is Bernoulli random variable. So let's that each flip is a Bernoulli random variable x. So x can take only 2 values, 1 and 0, which is given. Bernoulli random variable is given by this. Theta is the probability is theta if x is 1, and the probability is 1 minus theta if x is 0. So a1 is head and 0 is tail. So we are actually trying to find this theta then, because that is my question. What is the chance of head for my next flip? So theta is 0, 1 is a parameter to be defined from the theta between 0 and 1. So we can write this probability more succinctly as this. So if you all know that Bernoulli random variables can be, I mean, this probability can be written as this, because I mean, if you put x is equal to 1, this term becomes 1, so this term becomes theta. If you put x is equal to 0, then this terms becomes 1, and this term becomes 1 minus theta, which is exactly following this. So what is the general recipe? As I said, you find you assume the model, then you find the joint probability, right? So let us assume that you have flipped the coin a few times and we got these x1 to xn, which are either 0 or 1, either head or tail. The question is, what is the value of the probability of theta? So one could assume that it is the number of heads. So this is what I said, that I mean, intuitively, that's what we know from the beginning of our statistics class. But can we prove this following intuition that that this is correct by proving that guess this is the most likely values for the real theta? That's what I told last, right? Oh, sorry. So the joint probability is, of course, f of this. So which is, I mean, f you can think as just the likelihood function. I mean, L. So since I mean, I need to probably move those general recipe of maximum likelihood earlier, so that these notations are a little bit more compatible. But yeah, let's go ahead with it. It's just the joint probability distribution, which is the product of this. Then if you put your Bernoulli random variable succinct form, it will come in this way. So this is the product of them. So the powers get summed and so on, right? I mean, this is algebra. I'm not going into too detail of it. And then you will find the basically the minimization of. So this is the last slide. We are now want to find theta, which makes this probability the highest. It is easier to maximize the log of the joint probabilities, which is log L theta. So I think I have made a mistake in the notation. So this should be really L. This is not F. This is not F. I'll correct this. And this is, if you take log, of course, the powers come here and so on. Then you just do the basically gradient computation. And if you make it equal to 0, you will find this form, this whatever your x is, and the sum of it, and by n, right? I have gone a little fast today, but this again I'll come back. So I'll start from this example tomorrow. So if you have any questions, you can ask. I'm seeing someone says linearly independent columns. So whose linearly independent columns, etc., that you need to find, right? What does it mean? How you certain is it from the hyperplane? So Rishabh, I think you had some questions, which I said about when I gave the example of that. Suppose you are a real estate practitioner. So what do you mean by how certain from the hyperplane? Hopefully that is clear. If not, please ask.
Yeah, so actually I was asking, I mean, there was a term called how we are finding hyperplane as a best fit for the regression problem. Now we are asking how uncertain it is from the hyperplane, and what does it mean?
Yeah, I gave you one example, right, about that real estate price. So if you are going into, okay, where was that? Yeah, so if you are, so see that initial, I mean, earlier in the non-probabilistic formulation, what we were doing is we were assuming it only this. So you are giving like theta 0 plus theta 1 x1 plus theta 2 x2 and so on. So if you find theta 0, theta 1, theta 2, etc., that is the whole theta, you will be able to give the y1. Or for a particular x star, you will be given the y star. That is for, say, the x components in square feet, the x2 components in number of rooms, x3 components in the age of the building, you will be able to give the y star. But you can't say that, okay, y star is say 20 lakhs. But you can't say that, okay, it is 20 lakhs plus minus 1 lakh. That plus minus thing you will be able to give by this sigma. And that in that figure is, I mean, yeah, it's not in this figure, but sorry. It is what is meant by the uncertainty, that, okay, I'm giving you a value, but how uncertain is that I am also quantifying, right? Okay. Shubham, you have some question? I see some, yeah.
Sir,
Mm-hmm.
Sir, in the maximum likelihood, what in let's say in the simple linear regression, we just give the training example and we try to define the cost function and we try to minimize that cost function and find the theta values. But sir, in maximum likelihood, what I have to do, I didn't get it.
Yeah, you need to. So I have given you the recipe. I have not told like how does that recipe fit into here. We will come into there tomorrow. But if you are interested, of course, you can go into the slides. I mean, it is there. Here, let me go. So maximum likelihood for linear regression. You see, I have not covered it, but the recipe is given, the problem setting is given. I just have to fit this problem setting into the recipe. I would request you just read ahead. We'll again cover tomorrow. Or not again, I mean, we'll cover it tomorrow.
And sir, one more question, sir. Here the distribution, whatever the Gaussian distribution you are using, the parameter we are going to use two parameters. One is theta and another is variance. And the theta will be act as our mean.
Yes, because we have assumed zero mean Gaussian. So that is the property of the Gaussian, right? So if it has like some mu as the mean, then your prediction will be theta plus mu, right? So Gaussian has those properties. So if you are adding to a constant the Gaussian noise or Gaussian variable, then what does, and the Gaussian, suppose the Gaussian has mu and sigma as your mean and variance, then what is the form of the output of the sum? Is it a Gaussian? And if it is a Gaussian, then what is the mean and variance of it? If you
I
add,
will read. I will read.
you have to read the Gaussian.
Okay.
It will be just the mean of the Gaussian and the variance of the, sorry, the mean of mean value of that constant, or basically the constant. So mean value of the constant is the constant. And if the Gaussian has a mean mu, then it will get summed, and the variance will be sigma square. So yeah, just read the Gaussian random variable a little.
Okay, sir. Thank you, sir.
I see no raised hand. Okay. If there is any other question, otherwise I'll just stop here today. Something is that, if you have any logistics related question, so I will upload that last week's video. I mean the